Hello all, welcome back. Today we will be continuing with our previous topic, that is liquid propellant rocket motors. And my name is Sai Krishna from the Department of Aeronautical Engineering from the Institute of Aeronautical Engineering. And in the previous class, what we have discussed are basic phenomena, in particular liquid propellant rocket motors. And continuing the same, we will be discussing regarding the propellant tanks. Now, as in liquid, particularly liquid propellant motor system, what we are having bipropellant system. That is, your fuel plus liquid oxidizer will be stored in a separate tanks and they are pumped onto your combustion chamber for combustion. Now, the propellants are stored in separate tanks. Now, coming for your monopropellant engines, where we'll be having only one propellant tank which contains either with the fuel or oxidizer. Right? Now, what is basically the monopropellants are? Basically, they are having high reactive or highly corrosive propellants which are reactive in nature as soon as they are expanded. Right? So as soon as they expand, we will be getting the required amount of thrust at that specific instant of time or specific period of time. Our best example for that is my hydrazine. Right? Now, there are usually one or more high pressure auxiliary gas tanks, right, where a gas, particularly an inert gas, is being used to pressurize the propellant, and the tanks can be arranged in variety of ways, and the tanks can be varied based on their design, based on the shape, based on the location, and can be used to apply some control over the change in the location of the vehicular central gravity. Now, the figures shows you a simplified sketches that are typical tank arrangements of any large turbopump fed liquid bipropellant rocket engines. Now, if you are considering for a spherical tanks, what can we make? Rather than keeping one beside the other, we are arranging in a tandem, that is one above the other, because these can fit basically within the aerodynamic shape of my rocket engine. Now, coming to your small spherical tanks, particularly the sphere is good, but it is not consistent with holding out the more amount of fuel. So, in order to cope up with that, what we have done, we have basically created two sets of tanks, particularly with spherical ends but cylindrical in nature. Now, these will have either with external or internal piping, that's depending based on the type of fuel and type of oxidizer we consider, and they are positioned one over the other. That is a tandem arrangement. This is the same case but with an internal piping with common bulkhead as well as tandem tanks. Now, coming for concentric tanks. Concentric tanks are two tanks. Just a second. Two tanks particularly that are concentric in nature. Right? Now, the central tank will hold the fuel, whereas other will be oxidizer. Now, this type of arrangement can be used for all of the rocket systems, but only thing we are supposed to take care is of your stoichiometric ratio or your your fuel to oxidizer ratio. Right? Based on this, we can be able to select the orientation as well as the size of tank and the number of tanks. Now, coming to the last, which is my multi-tank. What happens under multi-tank is basically you will be having n number of tanks that are connecting multiple of my rocket engines. Now, based on these, right, these multiple tanks can be configured based on the requirement of your fuel to oxidizer ratio, that is 3 oxidizer and 6 fuel tanks, or 6 oxidizer or 3 fuel tanks, based on the type of propellant combination that we consider. Now, what is the advantage on the multi-tank? One advantage is basically as soon as one of the tanks get utilized, similar to my space shuttle rocket mission or SSME engines, space shuttle missions, what we are having? We are having an orange color external tanks. What these do basically, as soon as the propellant is being used up for the whole tank, it is jettisoned, right? Jettisoned during the flight path, which enhances the overall performance of my space shuttle. Now, in the same case, if we are considering for all the other previous tanks, what happens in this is basically as soon as the tanks gets discarded, as soon as the tank gets emptied out, then we are supposed to jettison them as a stage, right? As a stage, let's say primary stage, second stage. As soon as we jettison, the overall performance might increase in these four cases. Whereas for multi-tank, we can jettison individual tanks, but only thing we are supposed to take care is of the plumbing system, right? Plumbing, particularly the piping system. The piping system behind it will be more complex because we will be opening up or we will be removing part of a tank in between a flight, and that has to be compensated from other available tanks. Now, because the propeller tanks that also have to fly, their mass cannot be neglected and the tank materials are highly stressed. The common tank materials are aluminum, stainless steel, titanium, alloy steel, as well as fiber reinforced plastics with an impervious thin inner layer of metal to prevent leakage to the pores as well as the fiber reinforced walls. Now, why we are selecting your aluminum or any other steel? Basically of durability. First thing is of durability. In terms of what? Basically to hold the fluid, right? To hold the fluid that is onto there. Next, now as we are creating more, right? Particularly if you are going for cryogenic and every others, they tend to have more pressure at the ambient temperature itself or ambient conditions. So in order to withstand that, what we can do, we can add up more amount of material, particularly the aluminum or stainless steel, whatever, to enhance the structural strength of the tank, or we can change ourselves to the fiber reinforced plastics, particularly FRPs, with a coating of a thin metallic layer. Now, what happens with the plastics? Plastics which is porous in nature, which has lightweight and good strength. But coming to its integrity, particularly the durability to hold the fluid, they lack something, right? They lack the ability to contain fluid over a period of time, particularly the fluids under cryogenic temperatures. So, in order to cover those, what we are doing, we are reinforcing the same plastic wall, particularly FRP plastics, with a thin layer of metal to maintain the same structural strength. Any gas volume that is above the propellant tank is sealed tank is called an ullage. It is necessary that allows for thermal expansion of propellant liquids and for accumulation of gases that were originally dissolved in the propellant or for some propellants. For gaseous products that are slow, any slow chemical reactions within the propellant during the storage. Now what happens, let's say if you're storing anything, for example, a simple example is, let's say we'll hold a Coke, right? What happens to a Coke when we store under cold or low temperature? Basically, what happens, the gases that are dissolved in the Coke will not come out. Now as soon as you shake it or you store it in ambient temperature, what happens, as soon as you give the gas that is being present inside the Coke tends to move out based on the temperature or the ambient condition that it is on, right? Now coming to your propellants, as the rocket, right, as in a complete tank, small portion is always left unfilled, any propellant tank. Why? Because in order to cope up with the evaporating gases that are coming out from the tank, or if any reaction did takes place, right? Any reaction did takes place or any thermal expansion for the liquids happens, that particular area is left out for the fuel or the oxidizer to expand itself. Now, maintaining the same, if what if in case of hydrogen, right, particularly cryogenic, right? Under cryogenic, these will be fueled, right? These tanks will be filled only during at the launch, right? Now, as we can see for any other Starship or any other uh, Vulcan launches, everything, as soon as the propellant is being filled, you can see a small white smoke, particularly hydrogen propellants, hydrogen propelled rockets will be having some white smoke that is coming out of my rockets. This can be experienced or visible under our ISRO vehicles also. What is this basically? The liquid is being filled from down, right? So as the level increases, there is more room or area where the expansion of the same propellant takes place. Now the same expansion will take place. The expanded gases that are inefficient will be expelled out through the vents, right? That is your actual white smoke that you can see under your rocket launches. Now, depending on the storage temperature as well as the range and the propellant coefficient of thermal expansion and on particular application, the ullage volume usually ranges between 3 to 10% of the total tank volume. And once loaded, ullage volume and if not vented, the pressure also will change the bulk temperature and the density for the stored propellant that varies. The expulsion efficiency of a tank or a propellant piping system is the amount of propellant that can be expelled or available propulsion divided by the total amount of propellant that is being initially present. And a typical value that ranges from 97 to 99.97, because the losses that are consistently available of unavailable propellants that are left in a tank after rocket operation, that are traps in between the grooves or in between the pipes, any corner of the pipes, any filters, valves, everything, right? These are all retained by the surface tension of the propellant itself, right? Such residual propellant is not available for combustion in the combustion chamber and must be treated as inert mass, causing the vehicular mass ratio to decrease slightly. And in the design of tanks and piping systems, an effort is made to minimize such residual propellant. An optimum shape of the propellant tanks is also for gas pressurizing tanks is spherical, because for any given volume it results in tank with the least mass. Small spherical tanks are often used for reaction control engine systems where they can be packaged with other vehicular equipment. Unfortunately, larger the spheres, which would be needed for the principal propulsion system, do not fill up all the available space in the flight. Therefore, the larger tanks are often made with an integral with the vehicular fuselage or the wing. The most cylindrical with half ellipses at the end, but they can also be irregular in the shape. The cryogenic propellant cools the tank wall temperature far below the ambient temperature, and this causes the condensation of the moisture of the air surrounding the tank's exposed sides and usually also the formation of ice during the prior to launch. The ice formation is an undesirable because it increases the vehicular inert mass or the launch mass. Also, as the pieces of ice are shaken off or tend to break off during the initial flight, they tend to damage the vehicle, right? Particularly, and the best example is your any bottle or any cold water bottle that is being kept under ambient condition, particularly a humid condition. What happens after a certain duration of time? We can observe small droplets, particularly the droplets of the water onto the bottle. Now, if you maintain the same conditions in your cryogenic, what happens? The fluid that is contained inside the tank is colder, right, than the atmospheric air that is present out. So, as there is interaction between them, the water vapor that is available in the atmosphere will condense onto the surface of my rocket, right? right? They they tend to condense on the surface of the rocket, which for an initial rocket mass is high. Now, whenever a rocket is being launched, particularly we can see the ISRO or GSLV satellites launch vehicles, what we will be seeing? We will be seeing small scales of ice that is being dropping off from the rocket tip or at the rocket near to the nose. Now, based on this, what happens? They tend to drop off, right? These ice tend to drop off. If the ice is not much to be formed, it is acceptable. If there is a huge amount of ice formed, then they tend to destroy or damage the vehicle, particularly during at the launching or deorbiting stages. And for extended storage periods, cryogenic tanks are usually thermally insulated, means no thermal interaction from the atmosphere or the surrounding to the tank. Any porous external insulation layers have to be sealed to prevent moisture that is being condensed inside the insulation layer. And with the liquid hydrogen, it is even possible to liquefy or solidify the ambient air on the outside of the fuel tank. Even the best thermal insulation and a low conductivity structural tank support, it has not been possible to prevent the continuous evaporation of cryogenic fluids, particularly liquid hydrogen, and therefore they cannot be kept in a vehicle more than perhaps a few days without refilling. For the vehicles that need to be stored after filling or to operate for a longer periods, a storable propellant combination is preferred, particularly prior to loading any cold cryogenic propellant into the flight tank. It is necessary to remove or evacuate air from the tank and propellant passages to avoid forming solid air particles and ice from any existing moisture that is being predominantly available either in the tank or the piping system, because these frozen particles would plug up the injection holes, particularly towards the combustion chamber, and cause valves to freeze and shut, or to prevent the valves from whenever we are telling it to be fully closed. The tanks, pipings as well as the walls are also need to be chilled or cooled down before they can contain the cryogenic liquids without excessive bubbling, particularly to let it for evaporated faster. And this is usually done by admitting a small initial amount of cryogenic liquid to absorb the heat from a relatively warmer hardware prior to the engine start. And during this initial cool down, the propellant is vaporized and vented through appropriate vent valves and is not available for propulsion. But when a tank or any segment of a piping containing a low temperature cryogenic liquid is sealed for an extended period of time, what happens? The ambient heat and ambient temperature surrounding the same hardware will cause the evaporation, and this will greatly raise the pressure inside the tubing, and this which may exceed the strength of the sealed container, particularly the tube. Now, the controlled self-pressurization is difficult to achieve. Uncontrolled self-pressurization will cause the failure as well as the major leak or even a tank explosion. All cryogenic tanks, particularly, and piping systems are therefore vented during countdown on the launch pad, equipped with the pressure safety devices such as the burst diaphragms or relief valves, and evaporated propellants are allowed to escape from it, right? And for longer term storage of cryogenic propellants in space or on the ground, some form of the powered refrigeration systems are needed to recondense the vapors and minimize the evaporation losses. What does this mean? Basically, in a container, if let's say on the ground or on space, as if you are maintaining some amount of propellant, the other amount of propellant will be filled by the same cryogenic gases, particularly in the form of vapor. Now, in order to maintain the same volume of gases, what we are going to do? The tanks will be subjected to the ambient condition, particularly ambient temperature, right, and ambient light. Now, based on this, what happens? They tend to move, increase, or expand themselves to form the vapor. As the vapor expands, we are supposed to initialize an artificial right? Not the natural. An artificial refrigeration or a cool down process to cool or maintain the temperature of the tank within the specified limit to minimize the evaporation loss of the same propellant. Now, the cryogenic propellant tanks are usually refilled or topped off just before the launch to replace the evaporator as well as the vented cool down propellant. When such tank is being pressurized just before the launch, the boiling point is slightly raised and the cryogenic liquid can absorb any heat being transferred to it during the several minutes of rocket firing. And during the flight, liquid propellant tanks are difficult to empty under side acceleration, particularly either 0 G or negative G conditions. So in order to recover that, what we are doing, we are using special devices or special type of tanks to use the same. Oscillations, as we have discussed earlier, the pogo or the side accelerations of the vehicle in flight may cause the sloshing of the stored liquid. That is very similar to a glass of water that is being jiggled, right? If you are holding a water on hand, as we tend to move the glass sideways, hand sideways, what happens? You can observe to the water. Based on the movement of my hand, the water tends to move either in that direction or in the opposite direction, right? Any one thing is possible. And if you're stopping that particular motion, and again water will slosh back to its same position over a period of time. Now, this sloshing effect, particularly when the tank is partly empty, sloshing can uncover a tank's outlet, particularly the liquid propellant, and allows a gas bubble to enter into the propellant discharge line. Now, as the gas is being entered into the turbo pump, the efficiency decreases as well as there will be a drop in combustion. These bubbles, which may cause a major combustion problems in thrust chambers, and the aspiration of the bubbles and uncovering of tank outlets by liquids, therefore must be avoided. Sloshing can also cause irregular shifts in the vehicular center of gravity, which makes the flight control a difficult task. Vortexing is another component that allows for a gas to enter the tank outlet pipe, and this phenomenon is similar to Coriolis force effects in the bathtub that is being emptied and can be augmented by regular spins or rotation in the flight. A series of internal baffles that can be used to reduce the magnitude of sloshing as well as the vortexing in tanks with the modest side acceleration. The positive expulsion mechanism that can prevent the gas from entering the propellant piping under multi-directional and major acceleration or spinning, that is the centrifugal acceleration. Both the vortexing and sloshing can also be greatly increased unavailable or residual propellants and thus some reduction in the vehicular performance. In a gravity-free environment of space, stored liquids will float around and is partly empty tank may not always cover the tank outlet, thus allowing the gas to enter the tank outlet or the discharge pipe whenever possible. So various devices have been developed to solve the same problem, that is a positive expulsion devices and the surface tension devices. What is a positive expulsion is a simple design with a movable piston or inflatable flexible bladders or thin movable or flexible metal diaphragms. Now, it's a small example for ullage bubbles that are randomly available under a zero gravity environment. What happens? This is my propellant, and in this case, this is my propellant. Right now, initially, let's say after out of a 10-second period of my flight in a zero G environment, the tank volume is of let's say around 70 to 80%. At that time, these are the bubbles that are being formed, right? As the tank empties out, right? The ullage or particularly the bubbles will coalesce, forming the larger amount of ullage, and the propellant will stick onto the surface of the tank. Now, what happens during this? Basically, as there is no gravity or no any force to push the propellant towards the outlet, they tend to be wasted in complete flight. Now, whereas coming for my other type, particularly a screen type surface tension that is being maintained out, where you are expecting this is your tank, right, and this is your liquid out or outlet, and you're pushing something in, particularly an inert gas or any other vapor of the same gas or same propellant, that is you are taking out. Now what happens during this, they tend to maintain the pressure, right, the pressure on the liquid, pressure on the fluid, to maintain the same, right. As the pressure is being maintained, it is constantly pushed out towards your combustion. Now, the surface tension devices, particularly such as 200 mesh screens, rely on the surface tension forces to keep the outlet that is being covered with the liquid. Alternatively, a small acceleration can be applied in a zero G space environment using supplementary thrusters. And in order to orient the liquid propellant in the tank, several basic type of positive expulsion devices have been used successfully in propellant tanks with pressurized feed systems. And these devices mechanically separate the pressurizing gas from the liquid propellant in the propellant tank. Separation is useful for these reasons. It prevents the pressurizing gas from dissolving in the propellant and the propellant vapors from mixing the gases. So any dissolved pressurizing gas which dilutes the propellant reduces its density as well. So its specific impulse and makes the pressurization inefficient. So that is the reason we will be using inert gases to reduce the overall solubility of the gas, that is the pressurizing gas, onto the propellant. If you use any other gas that is soluble in the propellant, the overall density of the same will decrease, which in turn affects my specific impulse upon combustion. Now, second one, it is moderately hot and reactive gases, such as generated by gas generators that are used for pressurization, that permits a reduction in the pressurizing gas system volume as well as mass. Mechanical separation prevents chemical reactions between hot gases as well as the propellant, and preventing any gas from the gases that are dissolved in the propellant prevents the propellant vapors from being diffusing into the pressurant lines and freeze, which reduces the heat transfer to the liquid. In some cases, the ullage of the tank containing toxic liquid propellant must be vented out without spilling any toxic liquid propellant or its vapor. For example, in servicing a reusable rocket, the tank pressure needs to be relieved without venting or spilling any potentially hazardous chemicals or materials. A positive expulsion device particularly permits the center of gravity to be accurately controlled, making its location known during its engine operation. This is important in rockets with high side acceleration, such as anti-aircraft missiles or space defense interceptor missiles, where the thrust vector needs to go through the vehicular CG, and if CG is not known, an unpredictable turning movements may be imposed on the vehicle. So a piston provides the sloshing as well as the vortexing. These are your simple sketches, particularly for three concepts for positive expulsion devices. Particularly first one is your inflatable dual bladder, rolling peeling diaphragm, or third one will be my sliding piston. Let us understand this. Right, the first thing, this will be a bladder, particularly an elastomeric bladder, that are created to expand when blown out, similar to a balloon. Now what happens to this? In a spherical tank, first initially we will be keeping a thin bladder which is connected to an internal tubing of pressurizing gas. Now as the rate of propellant is getting out, based on that we tend to push the gas inside the bladder. So what it does is basically expands, creating a small void at the center of the tank. Now as the void is being created, it pushes the fluid out towards the propellant outlet. Right? Now what is the main advantage in this? Basically, earlier under pressurized gas pressure fed systems, the gas whatever we are inserting onto your propellant tanks will be in direct contact with respect to the propellant tanks. So in order to maintain or to cover up the solubility for that, what we will be doing, we will be using a inert gases, which again requires an additional tubing, particularly plumbing system, as well as an additional form of tanks to carry those. Now, what happens in this basically, as there is a bladder, right, flexible bladder, they it the gases, it can be a gas generated gas or any other vapor, they do not tend to dissolve in the actual propellant, as there is separation between them using bladder, right? So as there is no dissolution, there will be a constant specific impulse that is coming out from a specified amount of fuel. Now coming to next will be my rolling peeling diaphragm, where the diaphragm is basically glued to the wall, right? Glued to the wall, and the propellant is being filled inside the tank. Now what happens under doing this is basically from one side of my diaphragm, not inside, outside of the diaphragm, we will be having input connections for sending out the pressurizing gas. The gas can be anything, right? As the volume of the gas decreases, we tend to pressurize the side of the diagram, which again pushes out the required propellant, right? Now continuing the same, if we are using for any piston with seals, what happens during this? Basically, the pressurized gas inlet will push the sliding piston, similar to your piston inside an IC engine. As they send out, the propellant is being expelled out, right? Pushed out of the cylindrical tank towards my outlet. Now, the surface tension devices, which uses capillary attraction, particularly to supply the liquid propellant to tank outlet pipe. And these devices are often made with very fine mesh, that is 300 mesh. Stainless steel wire moved into a screen and formed into tunnels as well as other shapes. These screens are located near the tank outlet, and in some tanks, tubular galleries are used to design to connect various parts of the tank volume to the outlet pipe sump. These devices work best in a relatively low acceleration environment where surface tension forces can overcome the inertial forces. A combination of the surface tension forces, particularly screen tension, screens, baffles, sumps as well as the traps, is called a propellant management devices. And during gravity-free flights, suddenly accelerated from a relatively large thrust, high forces can be imposed on the tanks, and thus the vehicle, by strong liquid sloshing motion or by sudden changes in position of the liquid in a partly empty tank. The resulting forces will depend on the tank geometry, baffles, ullage volume as well as its initial propellant location, and on the acceleration, the magnitude as well as the direction. Such forces can be large and may cause the tank to be failed. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.